In this lesson, we'll discuss titration using weak acids and strong bases. The question reads, a 40.0 milliliter sample of 0.100 molar HNO2 is titrated with 0.200 molar KOH. That's a strong base and that's a weak acid. We're expected to calculate the volume required to reach the equivalence point, the pH after adding 5.00 milliliter of KOH, and the pH at 1/2 the equivalence point. Let's start with question A. Here we're expected to find the equivalence point. That point occurs when the amount in moles of added base equals the amount in moles of acid initially in the solution. That being said, we begin by calculating the amount of moles of acid initially in the solution and the amount of moles of KOH that must be added, where it is equal to the amount of the weak acid. So let's begin with the weak acid. The weak acid being HNO2. Finding its moles is not hard. We'll convert this number into liters. We have 0.0400 liters. Multiply to its molarity, 0.100 moles per liter. This cancels out with that. We're left with moles. So 0.0400 times 0.100, and that gives us the following. So that's the amount of moles of this acid. Now, given what was said earlier, this amount of moles has to be the same amount of KOH. So the amount of moles of KOH must be equal to 4.00 times 10 to the power of -3 for the equivalence point. So in order for us to have a volume consisting of 4.00 times 10 to the power of -3 moles, we need to take this amount and multiply it to, remember this is the same thing as 0.200 moles per liter. That's in moles. So we'll flip this around where we have 1 liter at the top and 0.200 mole at the bottom. What this will do is cancel that out, and we'll multiply this to 1 over 0.200, and we get a volume of 0.02 liters of KOH. That right there answers question A. Let's move on to question B, the pH after adding 5.00 milliliters of KOH. So we want the pH after adding 5.00 milliliters of KOH. Remember that KOH completely dissociates into potassium plus OH minus. Of course, before adding KOH, there's no OH minus in the weak acid. So let's create a chart just to organize our work. We can write down OH minus plus this weak acid, which doesn't dissociate, HNO2 forms water plus NO2 minus. Before the addition, we have none of this, plus the amount of moles of HNO2, which we calculated to be right here. Let's rewrite that. 4.00 times 10 to the power of -3, and that's moles. We'll ignore this because it's a liquid, and none of that. After the addition, however, I'll write down AA for after addition, we are adding, let's see how much moles of OH. So we were told that it was 0.005 liters, and the concentration as given in the question was 0.200 moles per liter. So if I multiply these two out right now, let me show you. I end up with 1 times 10 to the power of -3 moles. And because it's a 1-to-1 ratio, the same amount of moles here. So I'll write that down, 1 times 10 to the power of -3. So this is how much is being added. And as you add OH minus, the amount of acid goes down. Remember, we're titrating here. So I'll take this number, 10 to the power of -3, and subtract it from the answer we found earlier. And we're left with, after the addition, 3 times 10 to the power of -3 moles. Now that we found this number, remember that HNO2 is a weak acid, and weak acids incompletely dissociate. This means that very little H3O+ will form, and the majority will still remain as NO2- ions. The hydronium ions, H3O+, that do form will react with the hydroxide, forming water as shown on the right side. And at the same time, this frees up NO2-. The amount of NO2- will be equivalent to the amount of hydroxide added, especially given the stoichiometric 1-to-1 ratio shown here. Once again, we ignore that, and over here, we can say that all of the OH- has disappeared, so approximately equal to 0. From here, we can use the Henderson-Hasselbalch equation to find the pH. So pH is equal to pKa plus log of base over acid. The pKa for HNO2 is 3.34 plus log of our base. Remember, this is our conjugate base, 1 times 10 to the power of negative 3 over our acid, 3 times 10 to the power of negative 3. If we substitute this all into our calculator, you should end up with 2.86. So that right there represents the answer to question B. Finally, in C, the pH at 1/2 the equivalence point. Remember what the equivalence point was as discussed earlier. That occurs when the amount in moles of added base equals the amount in moles of acid initially in the solution. So if we take a look at this, the amount of acid added was 4.00, and if we divide that by 2, since it's half the equivalence, not add equivalence, it would be this OH- instead of 1 times 10 to the power of negative 3 is 2 times 10 to the power of negative 3, because it's half of this number. So let's make a note of that. We are adding 2 times 10 to the power of negative 3. This means that this becomes halved, and everything else pretty much becomes the same thing. So using this formula again, substituting these two numbers into there and there, we get log of 1/1, which is equal to 0. And 3.34 plus 0 gives us a pH at 1/2 the equivalence of 3.34. And there you have it. That is what happens when you mix a weak acid and a strong base together in a titration.